Okay, so we're going to talk about the slope of a line and calculating the slope of the line. So we need to talk about, first of all, what exactly is the slope of the line and what does it mean? So we're looking at these position time graphs, which is basically distance time graphs. So we have time on the bottom, and then we have the position or the meters on the y-axis. So this kind of shows us what's going on. And remember, these are velocity graphs, okay? So what's happening here is in this particular situation, we have forward motion. In this particular situation, we have backward motion, and then again on the flats, we have no motion, okay? So that's the first thing we have to realize is this is not necessarily slowing down. This is not an acceleration graph. This is a velocity graph. So this is moving into a backwards position. But the slope, meaning the slant or the steepness of the line, tells us how quickly something is moving. It gives us the average speed. The average speed is equal to the slope. If you remember from your math class, you were told that slope is the rate, or it's the change in distance, so the change in y. And so therefore, that does give us the average speed. All right, so slope represents the average velocity. Okay, slope represents the average velocity. However, remember that a negative velocity means that we're moving in a backward direction. It does not mean that we're slowing down. All right, so how do you calculate slope? So you probably remember from math, it's rise over run. And the rise over the run is going to give us the change in y, right, over the change in x, right? So you'd say y2 minus y1 over x2 minus x1. If you get a positive reading, then you are moving in a forward direction. If you get a negative slope, then you are moving in a backward direction. So you may be going south instead of north, or west instead of east, or left instead of right. Okay. All right. So what are the units for slope? Well, the units for slope depend on what the position in time is measured in. So in this particular example, the position is measured in meters and the time is measured in seconds. So since y goes over x, it's going to be meters per second. That's going to be our units for this particular graph. If it was miles on the y and hour on the x, it'd be miles per hour, or so on and so forth. All right, so looking at this graph, the other thing we have to realize is, just like everything else, our data in lab and our speed is not necessarily going to be constant. There's going to be some changes. If you notice, we kind of have a little bit of a curve here, a little bit of a bump here, then it looks like maybe a speed up really quickly and maybe a drop down. So that's the reality of how data works. So what we have to use is a best fit scenario. It's something that's going to show us the trend. So we're going to use a straight line here to represent the average or this trend of how things are going, so that we can do our calculations and get some more information. Now, if we have a straight line, we have a constant velocity, constant slope, constant velocity. Again, remembering that if we have a positive slope, we are moving away from the starting point because we are increasing the distance from start to wherever we're heading. We have a flat line, we have zero slope, which means we have zero velocity. That is standing still. We're not moving forward, we're not moving backwards, we are standing still. And remember that if we have a straight line down, it doesn't mean that we're slowing down. It means that we are moving backwards, or we're going towards the starting line. We are decreasing the distance between the starting point and our position. All right. So at this point, we want to know what point is velocity decreasing, okay? And this is a little bit misleading because if we notice, velocity is actually decreasing here, but it's not because it's negative, right? It's actually because the slope here is not as steep as the slope here. So you notice if you take from if you take this position to this position, notice that we have a steeper slope than if we take from this position to this position. That means steeper slope, greater change in the y. So we have a steeper slope here, so our average speed is greater, right, than our average speed is right here. So even though it is the decline, or if you will, going back towards the starting point, the decreasing velocity or the decreasing speed actually comes from the decrease in slope, the smaller slope. Again, remember that this flat part right here, we stopped, okay? So here it looks like we're standing still for a minute. We get started, maybe a bit of a slow start, but then very quickly, then we're moving back towards the finish line or the starting point, but this point we're moving slower. See how it takes us 4 seconds, right? 4 seconds to cover the same distance that we covered in 2 seconds here. And that is where the decrease or decline in velocity comes from. All right, so best fit lines, just like we talked about, this is how we are going to work with our best fit lines. You're going to get your data points and you're going to plot your data points, okay? Then once you plot your data points, you're going to actually take your ruler by hand and draw a line that fits best, meaning that it goes through the most points and is closest to the most points. Now, you are going to have to eyeball this, and everybody's is not going to be exactly the same, but they should be relatively close, okay? Then once you do that, take 2 of your points that actually fall directly on the line. Don't take the points that are above or below. Find 2 that actually fall directly on the line, and then use those to actually calculate your slope. And that's going to be the average velocity of your travel, of your trip. Okay, and that's called a best fit or trend line. And that's what we're going to do for our graphs as well.